Okay, let's continue. As I said on day 2, magnetic recording is the field from which spintronics grow. Okay. So, many of the inventions from magnetic recording gave rise to the spintronics phenomenon, and the magnetic recording is the one area where spintronics was first applied. Okay. So, we are using spintronics based read sensor for reading information in magnetic recording. So, just for 1 or 2 sessions we will touch on magnetic recording before we move on to hardcore spintronics. Okay, so, for the next few minutes we will focus on magnetic recording. Magnetic recording was first invented in late 1890s. Then people started using magnetic recording for audio, so for recording voices. Okay, then somewhere in 1950s, particularly 1956, IBM came up with a hard disk drive for mainframe computers. Okay. So, this was in 1950s. Computers were used in mainframe computers. Then somewhere in 1980s, desktop personal computers became popular. So, hard disk drives were invented for desktop computers. Then laptops started using hard disk drives. Then, as I mentioned a few days ago, Apple introduced iPod, a music player with a hard disk drive for music files. So, we could play like thousands of songs using one device, which was revolutionary at that point of time. Then gaming applications like Xbox started using hard disk drives. Then somewhere in 2005 later on, social media applications like Facebook, YouTube all came into picture. So, they started storing information. Now, we use cloud and personal storage and so on. Okay, so, this is how magnetic recording has been useful and is still useful. Okay, moving forward, where we will require hard disk drives. So, one application is like autonomous cars. So, you know that Tesla can drive on its own. There are many autonomous cars coming into picture. So, they have lots of cameras, they capture video. So, all these generate lot of data. Okay. So, roughly 4 terabyte of data is generated every day. All these need to be stored somewhere. So, that is one application. And if you look at this video, in other ways it should work. Yeah, okay. Not playing. Right? Okay, maybe I play another video. Not here, another video. Okay, let's go back to the slides. So, the video you saw is coming from a technology called True View Video Technology. Okay, it is coming from Intel. I do not know whether you have noticed in IPL 2021 or 22, there was this technology. So, you remember, I remember Suresh Raina playing some shot, and that was shown in different angles. Okay. So, in this technology, what they do is like they place multiple cameras around the ground. So, each camera captures the video, then you can choose to watch which camera you want to see. Okay. So, by choosing the video from any particular camera, you can watch the game at a totally different perspective. So, imagine like having say 10-degree one camera, you have 36 cameras, and all these cameras are capturing information at 4K or 8K HD. So, they are generating lot of data. Okay. So, you want to store all this data. Okay. So, future it is going to be like everyone is going to generate data, and we need some device to store information, and solid state drives are more expensive. Hard disk drive is the cheapest way of storing information. So, that brings us into why we need to learn about magnetic recording. Okay. So, today we will learn about some basics of data storage. So, quite often there will be many new terms. So, I need to bring some analogy to introduce the data storage concepts. So, here I will use book as an analogy, because book we store information, right. So, it is a data storage, not electronic device, but it is a system that stores information. So, the magnetic recording people will always use the word medium or media. So, basically when we say medium or media, that is something where the information is stored. Okay. When we say medium or media, that is the place the information is stored. So, if you take book as an example, so in book we use paper to store information. So, paper is the medium, and any data storage system that you create should be able to store information, and we should be able to write information. Okay. So, there should be some ways to write information. So, in the case of paper or book, we use ink to print, or we use pen to write information, and there should also be some ways to sense the information. Okay. Otherwise, how do we know that there is information? Okay. So, there should be some ways to sense information. In the case of book, we use our eyes to sense information. Okay. It is not enough, we should also have some ways to interpret the information. Okay. So, you can look at all these letters, you can read information and interpret what I have written here. So, you have been trained to read English, and your brain has been trained to read English. So, you know. Okay. But if I show you something, then you do not know, even I do not know what it means. Okay. Because we have not been trained in Chinese. Okay. So, all these are important. So, when you talk about a data storage system, we are talking about having a medium to store information, we are talking about some ways to write information, we are talking about some ways to sense information, and there should be some ways to interpret the information. So, you have a data storage device, you have a computer. So, the information has to be passed from the data storage device to computer in a meaningful way, okay, in an interpretable way. So, typically this part of magnetic recording is done by electrical engineers and mathematicians. So, they do some coding, signal processing, mostly mathematics with some electrical engineering concepts. to interpret the information. So, we will not learn about this. We will also not spend too much time on how do we write information, particularly when it comes to magnetic recording. But when we are talking about memory, MRAM and so on, we will be learning about all these concepts. How do we store information, how do we write information, how do we sense information, we will learn all this when we learn about MRAM. But when it comes to hard disk drive, we will not spend much time here. We will spend more time on how do we sense information, because this is based on spintronics principle. But I will give you some brief idea how do we store information in the hard disk drives. Okay. So, I will be showing this triangle quite often, almost every day I will show this triangle. Okay. From now, every day I will show this triangle. So, we will be talking about how do we write, read or store information. So, in the case of book, we use pen or pencil to write information, we sense information with our eyes, and we store information on paper. Okay, so, if you take rock carvings, for example, we use nails to write information, we use our eyes to read information, we use rocks to store information. Okay. That brings us to the book lab part. Yeah, please scan. Okay, let us go move on to the first question. Okay, so only 10 of you are right, okay, and the correct 10 is this. Okay, so none of these which I have listed belong to magnetic recording. So quite often people think that CD is magnetic recording or flash is magnetic recording. Okay, so first I want you to go away with the knowledge that none of them is magnetic recording. So, if you take CD or DVD, for example, we have a disc. So, in that disc we have some material. So, that material has the property to go from amorphous to crystalline or crystalline to amorphous. So, we just learnt about amorphous and crystalline materials, right. So, this material, for example, if you heat them slowly and cool slowly, you will have crystalline structure. If you heat them and cool rapidly, it will become amorphous. Okay. So, by the way in which you heat and cool, you can transition between amorphous and crystalline phases. So, the reflectivity of the material will be different in the crystalline and amorphous phases. So, we use the laser induced heating to write information. So, we can go from crystalline to amorphous, amorphous to crystalline. So, you can call one of them as 0, another one as 1. So, we are talking about digital recording. So, from now we are talking about digital recording. So, we are only looking at bits 0 and 1. We are looking at 2 states, only 2 states. Okay, so, this can be 0, this can be 1. So, we can use the reflectivity. So, one of them will be reflecting more light, another one will reflect less light, or you can look at the phase change and read information. And storing is based on, I mean, these 2 states are equally stable. So, if you reach here, it will be stable, if you reach here, it will be stable. So, you can store information. And somewhere in 1990s, we had also magneto-optic recording, which is also not magnetic recording. And if you take solid state drives, they are using semiconductor technology. So, we are using the presence of electrons or absence of electrons inside a potential well to define 1 and 0. So, those are all not magnetic recording. So, when we talk about magnetic recording, we use these principles which I show in this picture to achieve magnetic recording. Okay. So, when we talk about writing information, we have an electromagnetic head. So, we learnt about electromagnet on day 2, right. So, I showed you that if you have a coil, you send current, you produce magnetic field, and if you have a coil and you place a magnetic material. So, in this case the blue color one is the magnetic material. So, that magnetic material will enhance the magnetic field, and we can generate magnetic field from this head. Okay. So, you can see that the blue lines are all magnetic fields. Okay. So, we can use these magnetic fields to write information. So, writing information is basically keeping the magnetic moments in one direction or the other, okay, something like this. So, we use an electromagnet to write information. So, in hard disk drives, these electromagnets are in nanometer scale. So, for example, this gap may be a few tens of nanometer, maybe 50 nanometer or even less. Okay. I am not very updated on what is the gap, but it is 50 nanometer or smaller. Okay. So, we are talking about tiny electromagnetic heads to write information in hard disk drive. And for reading, we are going to look at the magnetic flux that comes out of the hard disk drive. Okay. So, we have written some information. We have magnetized the material, it's in certain direction, they produce magnetic flux. So, we sense this magnetic flux as a way of reading information. Okay. So, for this purpose we will be using some magnetoresistive sensors. So, these are spintronics read sensors. Okay. So, we will learn about how they work later, but we use these sensors to read information. And for storing, we are using the coercivity. So, you know that once you magnetize certain material, the coercivity or the anisotropy energy keeps the magnetization in certain direction. So, once you have magnetized material with the north pole here, south pole here, we have learned that they will be stable for long period of time, and we are using this KUV to store information. Okay. So, this is how the magnetic recording works, and this is how a hard disk will look like, hard disk drive. So, if you open a hard disk drive, on the back side you will see something like this, on the other side there will be a cover, you open, then you will see something like this. Okay. So, on this side you will see a disc. Anyway, so this is the disc. So this is the disc that stores the information, and here you will find the head. This head is the one that reads and writes the information. Okay, so as I mentioned, the disc will be rotating and the head will be going between the inner diameter and outer diameter. So it can read or write over the whole disc. Okay, so this voice coil motor is the one that will make this one to go in this direction, and this motor, this spindle motor, is the one that will make the hard disk to rotate. Okay, so we have the disk, and this disk is the one we call medium. So this medium is the one that stores the data in hard disk drive, and this head is the one that reads or writes the information. And these chips that you see from Marvell or LSI, they are like the brain of the hard disk drive. Okay. So basically you have some magnetic flux coming out. The magnetic flux is converted into some electrical signal by the read head. Okay. So these electrical signals come to these chips. So these chips convert the electrical signal into meaningful information. So the computer understands 1 or 0, right. So this these processors are the one that will receive these electrical signals and pass them as 1 or 0 to the computer, so that your CPU can process that information. Okay. So this is a brief outlook of the hard disk drive. So let us watch this video and answer one question. Same video, you have watched this video before, but question is different. Okay. Okay, you may watch the video again. Okay, now answer this question. Okay, majority of you are right. Okay, the correct answer is magnets stick to the edges of a long magnet. So what does that mean? So when you stick many magnets together, so you can call that as a long magnet. Okay, that's what I have said. Okay, so when magnets stick to the edges of the long magnet, what does that mean? It does not go and stick in the center, right? So what does that mean? So that means the magnetic field is stronger near the pole. Okay. So when you have magnetic materials, let us say you magnetize them once. So, they have a pole. So, they have north pole and south pole after magnetizing, then they generate a magnetic field, and this field is stronger near the poles. So, if you count the number of lines per given area, you will find more lines here, same area you will find less lines here. Okay. This means the magnetic field is strong here, the magnetic field is weak here. Okay. So, this is the reason why that particular assembly of magnets, the magnets go and stick here, okay, here or here, because the magnetic field is stronger there. Okay. So, in hard disk drive, we are using this magnetic field that comes from the poles of the magnetized material to read or sense the information. Okay. So, this is the principle of reading. How do we read information? Basically, we are relying on the magnetic field generated by magnetized material. So, once you magnetize material, they will have a certain pole, north pole, south pole, and they will generate a magnetic field, and we are using those magnetic flux lines to sense the information. Okay. So, let us do another question. So, here I have two magnets. So, we can imagine that one of them is north, another is south. Let us say blue is north, red is south. Okay. So, I have arranged two magnets in three different configuration, okay, A, B, C. So, which okay, let us say I bring some sensor to sense information. So, this sensor will look at the flux lines and give me information where the flux is more. Okay. So, we have three different configurations A, B, C. Okay. I have used this color code to represent the poles. Okay. Now, tell me which configuration will generate the least magnetic flux. Okay. I will open this question. Okay, majority of you are right, very good, happy to see that. Okay, when you have magnets with opposite poles next to each other, what will happen? They will just stick together. Okay, so, when you bring them closer, they will just stick, there will be no flux coming out of this configuration. Okay. On the other hand, when you keep say south and south, or north facing each other, they will repel. So, basically the magnetic field produced by this pole, they will all go up, okay, or down. So, you will have more magnetic flux coming out when like poles are facing each other. In this configuration, they will just get attracted, nothing will come out, no magnetic flux will come out, this sensor will not see any flux. Okay. So, normally I carry magnets, I can demonstrate this, but when I travel I cannot carry, because sometimes they do not allow to bring magnets. Okay. So, you can do experiment, you have two magnets and find out some way to sense. Okay. Okay, so, this is the principle that we used for sensing information in some very old technology. Okay. So, we used a recording technique called longitudinal recording technology for many years, and in this configuration the magnets are placed parallel to the disc surface. So, we use this kind of discs to store information. Okay. So, when the magnetization of the material is parallel to the disc, then we call it longitudinal recording. Okay. So, in this configuration, as we just learnt, when you have two north poles facing each other, there will be magnetic flux, two south poles facing each other, there will be magnetic flux, and when you have two opposite poles facing each other, there will be no flux. Okay. So, now I am talking about a very old reading scheme. So, in this reading scheme, what they do is like, I mean, in computer you have clock pulses, right. So, there is a clock tick here, here, here and so on. So, there is a window between two clock pulses. So, during these two clock pulses, if the sensor sees some magnetic flux, okay, there will be some output voltage, and we call that as 1. So, during this window again there is some magnetic flux which will result into some voltage in the sensor, we call it 1. So, during this window there is no voltage, so we call it 0. So, here again the sensor gave voltage within this window, so we call it 1. Okay. So, this is how we read information in hard disk drive. So, the reading is based on the magnetic flux that comes out of the recorded bit of the recording medium. Okay. So, okay, I cannot bring magnets, but I can play this video to show what happens. Okay, so here you see I have stacked magnets. So, when they are sticking to each other, you know that this is north south, right. So, north south, north south, north south, something like this. Here I cannot bring them close to each other, because these are like poles, they repel. So, there is some distance here. So, this is a like pole. Here again is like north north, something like that. Let us say this is south south. Then here is north south, something like that. Okay. So, now I have this kind of sensor, So, this sensor can give rise to some light. If it, can you see a red light? Okay. So, if it sees a magnetic flux, it will show some light. Okay. So, depending on the polarity, it will show red light or green light. Okay. So, I move this sensor over this arrangement of magnets. So, you can imagine this is like bits of a hard disk media. Only difference is now these are like 2 centimeter long. Okay. So, in this demonstration your bits are in this particular demonstration your bits are 2 centimeter long. Do anyone know what is the length of a bit in current hard disk technology? Any idea? Guess some number. Huh? Nanometer, yes. How many nanometer? Okay, around 12 nanometer. Okay. So, in current technology, the length of one bit is 12 nanometer, but I am using a 2 centimeter magnet to demonstrate the concept. Okay, so, you are looking at the action in a bigger scale. So, this video is to demonstrate that the magnetic field will be seen only at the edges of 2 poles. So, when I have the sensor near the edge, there is light, no light, then only this edge you see the light, right. So, this is for this concept, that the field is stronger near the poles. Okay. Then this is the demonstration of recording at a larger scale. So, here again I am moving the sensor from one side to the other side. Edge there will be signal, but now you see there is no signal when it comes here, red, green, no light, again edge there is light. Okay. So, you can see that when the like poles north north or south south are facing each other, there will be a magnetic flux and we read information. Okay. So, this is a demonstration of reading from recording media, and here we are talking about a technology, very old technology. Okay. This is obsolete now. So, currently we are using another technology called perpendicular recording technology. So, in this case we are using thin films with a perpendicular magnetic anisotropy. So, we can magnetize the material to have the poles upwards. Okay. So, in this case everything will give some magnetic flux and we are sensing information. Okay. Then for storing is based on the energy barrier that we learnt. Okay. Let us say we magnetize a material down and along the easy direction, that is one direction where the energy is lowest, or you magnetize the material in the up direction. Okay. Let us say this is the magnet and it has 2 easy directions. Okay. Easy axis is along this bottle axis. So, magnetization can be either pointing up or pointing down, both are energetically low, and magnetization in any other direction, say pointing towards you, is a high energy. Okay. So, this energy barrier is the one that prevents the magnetization from flipping from one direction to the other direction. Okay. So, this brings to the question that you asked earlier. Okay. So, when you have many grains, when you have only one grain, the energy barrier is proportional to KUV, but when you have many grains, each grain will see some local field and that local field will reduce the energy barrier a bit. Okay. Yes. You mean this drawing before one? Okay. You don't understand this one. Okay. So, in longitudinal magnetic recording, you have a film, then on the you have a disc, on the disc you have film. So, in the film you have grains. So, those grains have easy direction in the plane of the disc. Okay. So, you magnetize them either pointing in one direction or the other. Okay. Whereas, in the case of perpendicular recording magnetization, you have film, the film has a perpendicular magnetic anisotropy. So, your grains have easy axis in the perpendicular direction. So, you can magnetize these grains to have magnetization up or magnetization pointing down. So, these two are the easy directions. Okay. All the other directions are hard direction. So, that is schematically is like having north pole of a magnet up or south pole of the magnet up, something like that. Okay, so, when it comes to storage of information, this energy barrier is the one that retains the information. I do not know whether you have learnt this terminology, volatile and non-volatile. Okay, we will go back to the other one. How many of you have heard these terms, volatile memory, non-volatile memory? Electrical engineer you will know. Then anyone else? Okay, you are all familiar, right? So, volatile memory means a memory which will lose its data when you switch off the power. Okay. For example, you take DRAM, SRAM in the computer or your mobile, they store information when the power is on, and once you switch off the power, the data is gone. Okay. So, when we talk about non-volatile memory, these are devices that store the information even after you switch off the device. Okay. So, when we talk about hard disk drives or devices like MRAM, magnetic random access memory. So, all these are non-volatile devices, which means they retain the data even if you switch off the power. So, what makes these devices to retain the data is this energy barrier. Okay, so, there is an energy barrier. So, this barrier prevents the magnetization from flipping from this direction to the other direction. Okay. So, if this energy barrier is very low, the magnetization may flip from this to this or that to that. So, the data may be lost, but if the energy barrier is sufficiently large, the data you write will be retained for long periods of time, and that helps us to achieve the non-volatility. So, you can imagine this energy barrier like let us say you have the ball in the bottom of this bucket, and if you want to transfer the ball from bottom of this bucket to the bottom of the next bucket, you have to spend some energy, right. You have to overcome this potential energy mgh, only then you can transfer the ball from one side to the other side. So, this gravitational potential energy prevents the ball from going from here to here. So, in a similar sense, the energy barrier, anisotropy energy barrier, prevents the magnetization from flipping from one direction to the other direction. Okay. So, that is what helps us to achieve the non-volatility of magnetic recording. Okay. So, when it comes to writing information, we use an electromagnet to write information. So, my classroom teaching, I usually carry this one. This is a tiny electromagnet. So, you send current through this coil, then you will produce a magnetic field along this direction. Okay. So, if I place a Hall probe which senses magnetic field, I can see the magnetic field. Let us see whether this video runs. Okay, this one works. So, you can see that I am applying certain current, then this field. So, when I connected the battery, the field is 0.27 millitesla. Once I remove the battery, there is no field. Okay. So, basically by sending a current through the coil, you produce a magnetic field here, and here I am sensing that magnetic field is a Hall probe. But if I have a disk media here, for example, let us say I have some disk where I need to write information, the magnetic flux that comes out of these poles can be used for writing information. So, we are using an electromagnet to generate magnetic field, and we use that magnetic field to magnetize the bits. Okay. So, in this case, for example, so in this demonstration I arranged the magnets physically. Okay. So, I kept the magnets like this. So, that is how I arranged the bits, but in a small disk like this, who is going to arrange the magnets? So, we are not going to physically arrange the magnets, but we are using the electromagnetic field to magnetize the disk to point in one direction or the other direction. So, the magnetic field from the electromagnet is the one that is going to determine the polarity of the magnets that you saw in the pictures. Okay. So, we use electromagnets produce certain magnetic field, and that magnetic field changes the energy landscape. Okay. So, I told you that at 0 field, this is how the energy landscape will look like, but as you apply more and more field, you can change the energy landscape. So, if this field is sufficiently large, this energy barrier will become 0. Finally, this will be the only stable state. So, the magnetization will switch. So, this is one way of explaining, but you can also use the hysteresis loop. So, we are applying a field much larger than the coercivity, so that we can switch the magnetization. Okay. So, we learnt about hysteresis loop, and the hysteresis loop parameters are related to the 3 concepts that we learnt, right. The 3 criteria are read, store, write. So, these 3 criteria can be related to the hysteresis loop parameters that we learnt. Okay. So, we learnt about MR. MR is the magnetic moment retained by the magnetic material even after you remove the magnetic field. Let us say you saturate, then you remove the magnetic field, you reach here. Okay. So, there is some magnetic polarity retained by the magnetic material. So, this is the one that generates the magnetic flux. Okay. So, basically if you multiply MR, the remnant magnetization of the material, by T, which is the thickness of the film. So, the MRT determines the signal for reading information. Okay. So, this part of the hysteresis loop, you can say it is related to the read property of the recorded information. Okay. So, we can say either the nucleation field or coercivity is related to the ability to retain information. Okay. So, if your coercivity is large, for example, then you cannot erase the information. Okay. For example, yesterday we were discussing about say putting MRAM into the pocket along with a magnet. So, magnet will erase the information, all those things, right. So, if coercivity is large, then your information will not be erased. Okay. If coercivity is small, the information can be erased. Okay. I can give you some example. If you take the old credit cards, so in the old credit cards you will see a black stripe. Okay. You will see a black stripe. So, this black stripe is basically a ferrite material with a coercivity of around 700 oersted. Okay, on the other hand, the magnets I have here, these are tiny neodymium iron boron magnets. Okay. So, you can see they generate magnetic field. So, these tiny magnets can generate magnetic field of around 2000 oersted. Okay. So, suppose I place a credit card on my pocket along with one of these magnets, then it is going to erase the information. Okay. So, now I can say this coercivity is not large enough to retain information. Okay, on the other hand, you take any contemporary hard disk drives, you buy a hard disk drive, the coercivity of your hard disk drives, I mean the material in your hard disk drive, like this. So, you have to fell down. Since when? This slide or this slide? Okay. Is it noisy? Yeah? Is it okay now? Okay, thank you. Okay, so before the mic was off, I was talking about coercivity being long enough, or I mean large enough or not enough to retain the information. So, in the old credit cards, the coercivity is small. So, a magnet that you keep in your pocket may be able to erase the information. On the other hand, if you take any contemporary hard disk drives, the coercivity is around 6000 oersted. Okay. So, you notice that this value coercivity is much larger than, I mean this is not coercivity, the field generated by the magnets, which is around 2000 oersted. So, 2000 oersted field cannot erase the information of hard disk drive, which has a large coercivity. So, you can correlate this coercivity to storage. Okay. So, if coercivity is large, then that material can store information without getting erased. Okay. So, you can relate MRT, MR multiplied by thickness to readability of hard disk drive. Okay. When it comes to writing information, this saturation field is the one that determines writability. Okay. So, if you remember this morning we were talking about Stoner-Wohlforth particles. So, we talked about having one particle versus having many particles next to each other. Okay. So, I told you if you have only one particle, this particle will reverse the magnetization exactly at Hk. Okay. However, when you have many particles, I told you that the hysteresis loop will be a bit different, because each particle will have some internal field coming from the neighboring particles and so on. So, because of the interaction, your hysteresis loop will be something like this. Okay. So, some particles, I mean half of the particles may switch at values lower than the Hk, but around Hk you can ensure that all the particles have reversed. Okay. So, in magnetic recording medium, we use this term Hs, which is the saturating field. So, we are very sure that at this particular field we can reverse the magnetization of all the grains. Okay. So, here you are reversing magnetization of half of the grains, whereas at Hs you are reversing almost all of the grains. Okay. So, we should apply a magnetic field larger than saturating field to write information. Okay. So, we can say that the Hs is related to writability of information. So, this is for reading. Okay, let me use another color. Okay, so, MRT is related to reading, coercivity is related to writing, storing, Hs is related to writing of information. Let us say your recording medium has a saturating field of 10,000 worsted, and if the electromagnet writer you have, it produces a magnetic field of say 20,000 worsted, which means you can write information onto this medium, no problem. On the other hand, if your recording medium has a saturating field of 70,000 worsted, and if your writer can only produce 20,000 worsted, then you cannot switch the magnetization of the material. Okay. So, Hs too large is not good, which means you cannot write information. So, you have some limitation in the magnetic field that you can produce with your writers. So, because of that you do not want too high saturating magnetic field. Yeah, okay. Okay, I will come to this point in a few minutes later. So far I am giving very simple picture. So, it is too early to answer this one. Let us do some questions now. Okay, majority of you are right. Okay, correct answer is 1. So, point D is related to remnant magnetization. So, I told you that the read signal is related to MR multiplied by thickness MRT. So, D is related to reading signal. Okay, correct. Next question is about point C. Okay, point C is okay, let me copy and paste the correct picture. Okay, you look at this one, point C. Okay, most of you are right. C is related to HS, saturating field, we learnt, and the saturating field is related to writability. Okay, so this is correct answer. Next one is about point B. Okay, all of you are right. Point B is related to storing information. Okay, before we move on to the next slides, I want you to, have a look at these things. So, on day 2 we learnt about substrates, right. So, these are the substrates that we use for hard disk storage. So, this is 95 millimeter diameter disk. So, this is the substrate used for the 3.5 inch hard disk drive, and this is the 65 millimeter substrate used in the laptop hard disk drives. So, 2.5 inch form factor, and this is aluminum. Okay, this is aluminum substrate and this is a glass substrate. Okay. So, glass is used because it is rigid, it does not cause any waviness, but aluminum does. Disc, if it is very thin and when you rotate at high speed, it can like cause waviness and it can cause crash of the disc. So, that is one thing I want you to have a look at, you pass around. Then secondly, we learned about target and magnets below the target. So, in this case I am showing you a target and the erosion profile. So, here we have symmetric magnets. So, because the magnets are symmetric, you can see a large portion of this target is eroded and we cannot use it anymore. Okay. So, that is one thing I want you to have a look at. The another thing that I want you to have a look at is like you can use this sensor to look at the magnetic fields produced by these magnets. Okay. So, this is the large scale demonstration of magnetic recording. So, you have a disc that has magnets pointing up or down. So, you have different lights indicating 0 and 1. Okay. Okay, so let us continue. So far I have been giving you a very simple picture that we are going to rely on this magnet arrangement to store information, and we are going to look at pulses produced by these fluxes in the rate sensors for reading information. Okay. So, this is okay if you are talking about big magnets at very low density. However, in the state of the art magnetic recording, I asked you a question, how long is one bit, right. So, currently our bits are like only 12.5 nanometer or smaller. Okay. So, each line that you see here, they are so close. Okay. We cannot use in this case I collected this picture using magnetic force microscopy, but in the state of the art recording technology the bits are so close I cannot take MFM picture. Okay. So, because the bits are so small and the data is tightly packed, the signals are messy, and they are so messy that the signals are almost analog. Okay. So, here I mean in the earlier picture I told you that we have this means 1, no signal means 0, right. Yeah, you can see very clear peaks, whereas in reality of the current technology, in current technology the signals are so messy that they are almost like analog. Okay. So, people do a lot of signal processing techniques to retrieve the bits, the binary digits from this almost analog signal. Okay. So, this answers the question asked by Moditma. So, in current state of the art technology, whatever discussion I made earlier are too simple. So, in reality like the signal will be somewhat like this. Okay. Let us say this is time and this is the voltage picked up by the sensor. So, you will have something like this. Okay. So, as a human we cannot say which is 1, which is 0, but the electrical engineers and mathematicians, they are very smart. So, they have come up with signal processing techniques to make meaning out of this. Okay. So, they can convert this into ones and zeros, for example. Okay. So, they produce ones and zeros from this signal and pass through the computer. So, this is the realistic reading mechanism. So, all the reading techniques that I gave you earlier, they are for understanding, but in reality the signals are very messy. I am thinking how far I should go. Okay, let us do something. So far I was giving you a very simple picture that MR multiplied by thickness is related to reading, coercivity is related to the storage, and saturating field is related to writability. Suppose I design 2 recording medium. Let us say I design 2 medium with desired values of MRT, coercivity and saturating field, and whether they will meet, they will give rise to the same performance. or not is the question. Okay. So, for example, let us say I have two medium A and B, MRT, coercivity and Hs are almost same, but let us say with the medium A I can achieve say 1.5. So, when I say performance, I am talking about how much information I can pack in a given area. Maybe the media A give rise to 1.5 terabit per square inch, media B may give rise to 1.6 or 2 terabit per square inch, something like this. Okay, so, you can see that the two media A and B I have made have almost similar values of MR, coercivity and saturating field, but the ultimate recording density that I can achieve in recording medium B is more compared to recording medium A. Okay. Why is it so? I told you that these three are the parameters related to the reading and the writing and storing, but still I notice that the recording medium A is inferior compared to the recording medium B. Why is it so? Why it could be so? I haven't taught you, so you can tell any answer. So, when you do the hysteresis loop, what is the typical size of your sample? A few centimeter. Okay. So, maybe like 1 centimeter by 1 centimeter. So, you take a small piece of sample, do VSM, then measure the hysteresis loop. Okay. So, you are getting properties of this particular sample over a very large area. Okay. Whereas, what is the size of the bit I talked about? Is 12 nanometer. Okay. So, the bits are like 12 nanometer long and maybe like 48 nanometer wide. Okay. So, we are talking about bits that store information at this kind of sizes on one hand. On the other hand, we are talking about properties like MR, coercivity, MS that we measure from a large area 1 centimeter by 1 centimeter. Okay. So, these properties that we measure at this scale will not represent what we say in this scale. Okay. So, micromagnetically the samples may behave different. So, whatever property that we measured from the VSM, they are macromagnetic properties because they are measured in a very large sample, whereas the bits that we are going to talk about, they are in the nanometer scale. Okay. So, if you really want to see how this recording media that you made will perform at high densities, we need to look at information in nanometer scale. Okay. So, people measure this information at nanometer scale using a device called spin stand. Okay, let me come back to that. Okay, before we go to that, so people do not just stop here. Okay. I mean, measuring these properties give you some idea whether your recording media A or B is good. Okay, if coercivity itself is like 1000 Oersted, for example, you can throw, right. You can say that this media is useless. Okay. So, you can use this to screen some property, but they are not enough. Okay. They are not enough. So, the people who make hard disk, they look at some more properties like signal to noise ratio, pulse width at 50% height, overwrite, thermal stability. So, many of the other criteria also needs to be looked at if you want to ensure that the recording media you designed works at high density. Okay. So, what made this recording media to achieve 1.5 terabit per square inch and this recording media to achieve 1.6 terabit per square inch is the difference in these properties. Okay. Signal to noise ratio, pulse width, overwrite, many of these properties gives rise to the fine difference between many different media. Okay, that is because so far I was giving you a very simple picture. So, I was telling you that we are using magnets arranged like this. So, I was using a very simple picture that one magnet stores one bit, okay. But in reality it is not the case. In reality, when you have a hard disk is made up of sputtered thin film. So, we are using sputtering to make thin films. So, the thin film is a polycrystalline material. So, we have lots of grains like this. So, we have a polycrystalline material with lots of grains and we are using them to store information. So, instead of one magnet that I described so far, we are not doing that, we are using a collection of grains to store one bit. Okay. So, the information is stored in many grains. So, that is why we have so many other things that we need to look at. Okay. So, when you do, I mean when you measure coercivity, all those things over 1 square meter area, maybe the properties of A and B average out. Okay. But when you are going at a small scale at the bit level, how these grains are arranged, they determine the signal to noise ratio and so on. Okay, so, if you take a hard disk drive, we have bits. So, if you zoom in the bits, the information is not stored in one magnet, but it is stored in a collection of many different grains. Okay. So, each tiny grain is like a one magnet. So, we are using a collection of magnetic grains to store information. Okay. And when you have a polycrystalline material, these grains are supposed to be random, right? You have no way to control each and every grain. Okay. So, there will be some easy axis dispersion or the grain diameter dispersion and so on. So, as a result, we also have some issue like signal to noise ratio. Okay, just show me a hand, how many here are electrical engineers? 1, 2, 3. Physics, or majority is physics. Okay. So, the physicist may like wonder what is signal to noise ratio. Signal to noise ratio is something that determines how reliably the information can be passed from one system to another system. Okay. Let us take this room as an example. So, here the information is coming from my side to your side most of the time. Okay. So, whatever I produce is signal. Okay. So, this signal is coming to you. So, you are all very quiet. Okay. So, noise is low. Okay. The signal is reasonably high. Okay. Signal to noise ratio is high. So, you can listen to what I talk. Okay. Suppose we go to the Guwahati railway station, then I try to give the same talk, you cannot understand because the noise of the railway station is so high that the signal to noise ratio is low. Okay. So, if signal to noise ratio is high, basically the information can be reliably transferred from one system to another system. If signal to noise ratio is low, we cannot pass the information reliably. Okay. So, that is basically a simple definition of signal to noise ratio. So, when we design a magnetic recording system, we want a high signal to noise ratio. That is one thing. So, we also want signal to noise ratio at high densities. Okay. It is not enough to have signal to noise ratio at low density, we want to have signal to noise ratio at high densities. Okay. So, I use this to show to my students. So, in some of my exams the students can bring cheat sheet. So, they can bring one A4 paper where they can write whatever they want. Okay. They can use that cheat sheet to write examination. Okay. So, they want to pack more information within this sheet, so they can cover all the questions. Okay. So, we just do not want to pack information, we want to pack as much information as possible in the hard disk drive. Right. So, like we do in a cheat sheet, we want to do the same thing. So, we want high SNR at high density. Suppose you write very small letters, but still you cannot make out, it makes no sense, right. So, you want to read the information from your cheat sheet, so that you can crack the examination. So, high density at high SNR at high density. So, this is what we want. Okay, in hard disk, whether in cheat sheet or hard disk drive, we want to achieve high density based on high signal to noise ratio. So, this is some example of the noise that we see in a magnetic recording system. So, I was showing you that the signals will be clean. Right? When I introduced you the concept of reading information, the signals are very clean, okay, but in reality you see this is the kind of signal we have. Okay, we have some signal, then you see the noise, even the peaks which correspond to the signal, they have some noise. Okay. So, this is what we get in reality. And this is at low density. So, here basically 18,800 bits per inch, whereas in current technology we are storing information at 2 million bits per inch. This is the kind of density at which we are storing information in the current hard disk drive. This is one example that I measured long ago. In 20,000 bits per inch itself, you can see so much noise, right. Imagine packing even more bits closer to each other, you will see more noise. Okay. So, we have to measure the signal, we have to measure the signal, we have to measure the noise, we can measure SNR, all these things we use a device called a spin stand. So, in this spin stand we have a motor that rotates. So, we place the disc. So, this is the disc you see here, this is the disc, and on the disc we can bring read write head. So, this read head write head will write information and read information. So, we can read the signal, we can measure the noise, we can measure signal to noise ratio using this device called spin stand. So, this is like a prototype hard disk drive. So, it is on a bigger scale. So, if your hard disk drive is like 1/4 of this size, this device occupies like this much area. Okay. So, it is a prototype bigger hard disk drive, where we can place our disk and read, write and measure the properties like signal, noise ratio and so on. Okay, so now the disk is rotating and the head is reading, writing information. So, you can see the plot of measured data. So, in the one side, x axis is a time, in the y axis you have the voltage. The sensor converts the magnetic flux into voltage, and that is what you saw. So, the pulses like this. So, this is coming from a perpendicular recording disc, where the magnets are like north south. Okay, now the density is higher. I am packing more density. You see the width is getting smaller. You can see more pulses now. Okay, I will play this again. Okay, so in this picture, x axis is the density at which I store information, and y axis is the signal to noise ratio. So, that graph you saw something like this. Okay. The signal to noise ratio keeps getting lower and lower as you pack more and more information closer to each other. As you increase density, the signal to noise ratio becomes smaller and smaller. Okay, for example, I talked about two different media, right, A and B. So, let us say I place the media A and B in the spin stand, and I measure the signal to noise ratio as a function of density. Density means how many bits I pack in a given inch. Okay. So, as I mentioned before, we need some critical SNR. Some critical SNR is reliably required for reliable reading of information. Okay. So, if the signal to noise ratio is below this one, is useless, we cannot read information. So, above this we can read information. Okay, so, I placed disk A and B, then I observed that in A, this is the density I can, this is the maximum density I can use. Okay. Whereas for sample B, the disk B, this is the maximum density. So, which one will I choose? Which one will I choose, A or B? B, right? Because B helps you to store information at high density. So, people do measurements like this Princeton to understand how the signal to noise ratio changes as you pack information at different densities. Then choose the disk that gives rise to high density, I mean high SNR at high density. Okay, so people do a lot of research to minimize the noise, increase the signal to noise ratio, and keep pushing this further and further. Okay. For example, maybe in maybe few years ago, the disk were like this. So, every year people try to push the limits of the hard disk drive. So, they keep increasing the SNR at high density. Okay. So, there is a lot of research going on, but we will not go into those details. Okay. Okay, so let me give a conclusion to the magnetic recording, because I do not want to go into the depth of this one. So, maybe like 2-3 minutes, then we can go for lunch. Okay. So, this is the concluding remarks for magnetic recording. So, we learnt about how do we write, read and store information. In magnetic recording. Okay. Then we also learned how these properties are related to hysteresis loop parameters like HS, MRT, coercivity and so on. Okay, then we learned that just meeting this is not enough. We also need to look at many other complex aspects like signal to noise ratio at high densities. And so on. Okay. So, the researchers who work on magnetic recording try to work on these finer aspects. Okay. These are like some qualification, I mean earlier qualification. To give you some example, right, I see many papers on magnetism. Okay. People will study some magnetic material which may have a coercivity of maybe 10 Oersted, okay, but still they will write in the introduction that magnetic materials are useful for magnetic recording and all those things. Okay. So, when a material has 10 Oersted coercivity, you cannot write that kind of introduction, because 10 worsted coercivity is totally useless for magnetic recording. Okay. So, we are talking about materials having 6,000 or 10,000 coercivity. Okay. And we are also looking at so many other aspects that determine how a magnetic recording technology will perform. Okay. So, people try to improve this signal to noise ratio, all those things. So, because of all these finer details, let us say you all saw a disk, right? So, the disk that stores the information. In the current technology, if you count the number of layers, there are many different layers. Okay. People use so many different layers to enhance the signal to noise ratio at high density and so on. So, there are many magnetic layers, non-magnetic layers with certain function, which is not scope of this particular course. Okay, there are so many layers deposited by sputtering. So, some of them are 1 nanometer, 2 nanometer, some of them are even like 0.8 nanometer and so on. Okay, there are about 20 or more layers. Okay. So far we were discussing magnetic recording as if we store information based on one magnetic layer, but in reality there are around 20 or more layers required to achieve high signal to noise ratio at high density. Okay. So, these layers are deposited in clean rooms of class 10 size, I mean class 10, I do not know how many of you know. So, class 10 means you take a small volume of space. So, within that space only 10 particles are seen. Okay. In this room, for example, there may be 50,000 particles in that volume. Okay. But if you go to a class 10 clean room, within that volume you will probably find 10 particles. Okay. So, people make all these discs in class 10 clean rooms using sputtering equipments that cost around 10 million US dollar. Okay. So, people spend so much money, so much technology to make the hard disk drive. So, when you buy a hard disk drive, you do not realize the sophistication that goes in achieving this particular technology. Okay. So, after doing all this, do you know what is the price in which the hard disk drive is sold for, one disk is sold for? So, after doing so much layer, so much research, so much physics, everything, one disk is sold at a cost of US $7, okay, of which the substrate itself is like $3 or $4. Okay. So, substrate itself is $3 or $4, then you spend so much research, then you make a profit of $4. Okay. So, we always say that this is the irony of research. Suppose you go to a shop, buy a frisbee, how much it is? A frisbee, right? Frisbee also is like $20. So, if you go and buy a frisbee, it's $20, it's just plastic, you mold it, press it, you sell it for $20 US. But with so much technology and physics that goes into hard disk drive, we are selling for just US $7. Okay. That is the irony of high tech industry. Okay. So, with that we will end this one, we move on to the other topics from tomorrow. Okay. Thank you.